Hello, and welcome to my presentation, Beyond the Hubble Constant, further results from fitting the ZDM distribution of localized fast radio bursts. So I'm Clancy James from Curtin University in Western Australia, but I am not the only person who's been working on this. In particular, in order to get the wonderful data we use from ASCAP, which is run by the CSIRO, Esan Mouli Ghosh and J. Xavier Prochaska have been helping me in leading this work, but there's a vast number of people who work as part of the CRAFT collaboration, who have contributed to taking the data and getting the redshifts of the host galaxies. And I'd like to thank all of them. But on with the thanks, what have we actually been doing with this data? So the data we fit have been, importantly, 16 localized ASCAP fast radio bursts, plus 60 unlocalized bursts with Parkes and ASCAP. And we've been using the dispersion measure, signal-to-noise ratio, and redshift, if indeed it's available. Now, we have to include the biasing effects of these observations, right? Include telescope beam shape, FRB width distribution, and the DM-dependent biases. And to model the expected values of dispersion measure SNR and Z, you have to model host galaxy properties, their contribution to dispersion measure via a log normal distribution, the fast radio burst luminosity function via maximum energy and cumulative slope gamma, and also the spectral dependence alpha. And we also have to include the source evolution, which we scale via a parameter NSFR. Needless to say, cosmology H0, right? We have to model that as well. And what we do is we put all this into a big 7-dimensional cube of parameters, derive the probability of these observations, and yield best fits via Bayesian methods. So the highlight is this is our final fit to data. X-axis, redshift, Y-axis, dispersion measure, extragalactic with the galactic contribution subtracted. The points are ASCAP FRBs that have been localized with known redshift, and the lines are the ASCAP FRBs with no host galaxies so far. The color scale here indicates a probability of observations. The dotted line includes 50% of probability, dot dashed 90%, and dashed 99%. And we derive a good fit. Now, the highlight of this fitting procedure is presented by Esan Mouli Ghosh in this talk, giving a constraint on the Hubble constant. Watch that first. Here, I'm going to talk about everything else. So very briefly, before going into the results, I'm going to show 2 slides on the model. I'm not going to talk about it in detail, except this shows how we divide up our dispersion measure contribution. It's a video, so please pause it now and take this in. And this slide here shows how we model the dispersion measure from the intergalactic medium. In particular, this is the expected value of DMIGM, also known as the Makar relation, whereas this describes the variance about that medium. Right, with that said and done, and you having paused and taken 5 minutes to take that in, let's get on with the first result. Right. Oh, and before then, I just want to quickly note this is what it looks like. In short, the blue line is a Makar relation. When you increase the Hubble constant, you decrease the slope of the line. And when you increase this feedback parameter F, you increase the spread about the line, or decrease it when you decrease F. Okay, so first result that is not on the Hubble constant is the dispersion measure induced from the FRB host galaxy. So this is modeled as a log normal distribution, the probability distribution of DM host, governed by 2 parameters, the log mean, right, in log 10 space, and the spread, right, the sigma host. Now, when you do this and you marginalize over the 6 other fitted parameters, the thick blue line is our result, right, which includes this pariah here on the Hubble constant, although the thin gray lines are for different pariahs. And you see, the result you get does depend on the assumed value of H0. The key point out of this is that the best fit median DM is 186 parsecs per centimeter cubed with this confidence interval. Now, that's the median of a log normal. The mean is about 400 parsecs per centimeter cubed, which is consistent with a CHIME correlation with large-scale structure, right, from this paper. And maybe the reason why CHIME see that and others don't is that CHIME have this increasing, and this is from their first paper on catalog 1, had this increasing sensitivity as a function of DM out to a DM about 1000 or so. However, all other modeling papers use a dispersion measure of 100 parsecs per centimeter cubed or less for the host galaxy. So maybe there need to be some improvements. The second important result is on the source evolution. So this is the number of fast radio bursts per co-moving gigaparsec per year. We model this relative to the star formation rate. So if you have star formation rate from Maddow and Dickerson, you scale that according to some power law, and then you account for this being a rate per year, right? So it's a 1 plus z scale. And what we find, therefore, is that n equals 1 means that the source population of FRBs evolves with the star formation rate. N equals 0 means no source evolution. And our best fit is n being 1.13 plus or minus about 0.45. In other words, it's quite consistent with the star formation rate. And we exclude no source evolution at 3 sigma level, right? Now, this still allows for a delayed subpopulation of, for instance, binary neutron star mergers. See Alexandra Morano's breaking news talk. And the other thing I want to point out is that we are not yet sensitive to this downturn in the star formation rate at high redshift. We're really picking up on this increasing rate here. Very briefly, I want to point out our results for the luminosity function. So we model this as an upper incomplete gamma function or Schechter function using Emax, right, maximum burst energy, and cumulative index gamma. You see the results here. Importantly, these are not super correlated in some cases with H0, while Emax is. And you see for gamma that the best fit is quite consistent with the slopes we see for individual repeating FRBs. Now, the final parameter I'd like to talk about are our results for the frequency-dependent rate. So when you talk about fast radio burst frequency dependence, there's two extremes. You can think of FRBs as being broadband, in which case you can model their fluence as a function of frequency via alpha. But if they're narrowband, you have to model them as a frequency-dependent rate, also as a power of alpha. The truth is complicated and some admixture of these. Here we use the rate model, right? Because it's computationally faster for various reasons. And because ASCAP observes in different frequency bands, this gives us some constraint on alpha. Now, we don't get good constraints in alpha. However, it is consistent with Makar's result for alpha of minus 1.5 or so, which scales to minus 0.65 for the rate model. Now, you might be asking, well, what about the chime rate? Because from Amiri et al. 2021, which was the paper from the DM dependence earlier, you'll see that as a function of frequency, the observed all-sky rate seems to be about constant over different experiments, right? However, if you look closely, you'll see that's an uncorrected rate, which does not account for systematic errors. Right? Now, if you have a toy model of those systematic errors, in particular, what is dominating the width of FRBs? Well, if the width is dominated by dispersion measure smearing in a band, then your rate, once you include the effects on signal to noise ratio and the consequent rate, even if the intrinsic rate is constant as a function of frequency, your observed rate will increase with frequency to the power of 2 and a bit. If it's dominated by scattering, it'll be even more. So you need an intrinsic rate that is increasing with decreasing frequency to compensate for these effects in order to keep this constant, right? So the rate of FRBs does increase at lower frequencies. Now, you might also ask, well, why do we spend of order 10,000 CPU hours on this big 7-dimensional fit? And the answer is because the Hubble constant is correlated with other fast radio burst parameters. So you then say, well, what happens if you do what others have done and you fix these parameters instead of fitting them and you would get the wrong value? So here the x-axis is different values of the various model parameters. Y-axis is H0, and what's plotted in the color scale is a probability distribution of H0 given that fixed value of the parameter. And you see that most of these parameters, except alpha, the spectral dependence, are quite correlated with the Hubble constant. Now, these correlations are quite complicated. I could spend a long time talking about them, but the message is you need to include the correlating effects of these other parameters in this kind of study. Now, it's also a little bit tricky when you go to select which data to use. So beware of repeaters, because many FRBs are only localized because they are repeaters. And these have different properties, whether or not their progenitors are fundamentally different. So we only use data from ASCAP localized FRBs, which are not derived from a targeted program. These are blind detections. You also have to be a little bit careful about fast radio bursts with no measured redshift. So if these have no measured redshift because of technical issues, that's fine, it's random data loss. But if that's because they're distant, for instance, you have this visible universe, but you can't see things further out, well, this introduces a bias in your P of Z DM distribution because you then only include this factor for certain values of redshift. So you need to deal with that by placing a cut on your dispersion measure and treating all FRBs with DM above that cut as unlocalized, and also including the PDM factor for those ones too. You can also ask, well, there's a lot of information going into this. Which bit of information is most important? So if you look at effectively the 5 different configurations of these 2 different telescopes, you see that the 2 configurations of 900 megahertz and 1.3 gigahertz with ASCAP, which have the most localized FRBs in them, have the best constraints in H0. However, there's one high frequency observation with a single localized FRB contains almost enough information on H0, sorry, units censored to not spoil Esan's talk, as the more than 20 FRBs observed with Parkes or CRAFT, which are unlocalized. So here, one localized FRB is worth at least 20 unlocalized FRBs. Now, there's also different statistics here, right? You have a joint distribution of parameters, which can be broken down into the probability distribution of the number of FRBs you observe, the ZDM distribution, and the signal-to-noise ratio distribution. And you see here that the number that you observe has almost no information on the Hubble constant, a little bit of information from the signal-to-noise ratio, and most information from the PDMZ distribution. But you can go further. This can be, in turn, be broken up into either saying, given you're an observer who detects FRBs with a certain DM distribution, what is the measured redshift given that DM? Or you can ask from a theoretical point of view, given some population of FRBs going off at redshift Z, what is the induced dispersion measure that those FRBs get after propagating from redshift Z? It turns out that the DM distribution on its own yields almost nothing, or almost no information on the Hubble constant, whereas the most is given by the probability of redshift given DM, which is effectively, in this PZ-DM distribution, taking this slice through here. Now, the last thing I want to point out is the effect of systematics, right? Because we are aiming to constrain the Hubble constant with FRBs, and that means we need to tidy these things up. In particular, the fraction of gas in the diffuse ionized medium has of order 4% error. We need to improve this. But how? The feedback parameter, in other words, to what degree is gas clumped in the universe, it's got partial degeneracy with DM host, and hence also the Hubble constant. We need to fit this as well, which implies a code speed up. Perhaps the most relevant one is the contribution to dispersion measure of the Milky Way halo. This is poorly constrained. It will vary by line of sight and has a significant effect on H0. Maybe Chime will tell us something more about this at this conference. And finally, the DM host contribution, there's currently no redshift evolution of this baked into that. Some simulations are available and we therefore need to improve the modeling. So in summary, FRBs can and do constrain H0. And to do that, it's important to model your observational biases and degeneracies with the FRB population parameters, but we get a lot more out. Fast radio burst population evolves pretty closely with the star formation rate. There's a much larger host galaxy contribution than all of you expect, and correlations with these parameters are important. And especially because in the future, we expect to get a statistical error on the Hubble constant of order 1 kilometer per second per megaparsec. It's going to be really important after we commission this cracker upgrade to fix the modeling, improve it, and reduce the systematics. Thank you very much for listening.